Hello everyone, thank you for coming. Today I'll be presenting to you about the mechanical design and fabrication of a kinetic sculpture with application to bioinspired drone design. This is work done by Andrew Lesser, me, Pravin Dengel, Akshat Singhal, and Professor Ramezani. We're all from Northeastern University, Silicon Synapse Laboratory, Boston, USA.
So I'll be begin with the introduction on Aerobat, which is the goal is to create a bio-inspired pet robot to achieve some untethered flight. So we developed this bat arm wing kinetic sculpture over here with some soft and rigid components. This is basically a single structure. The white is rigid component and black is flexible living hinges. So we implement this on this conceptual design over here on the Aerobat. This kinetic sculpture basically can bend such a way that basically we achieve a wing folding and expansion during the upstroke and downstroke. So this is done to achieve a more efficient flight by minimizing the negative lift during the upstroke motion, which I will explain in more detail in the next slide. So on the top image over here, it shows how the natural bat flapping gait looks like. The actual bat arm wing has 46 degrees of freedom, which way too many to mimic. And as you can see over here, during the upstroke, the bat folds its wing and it expands before the next downstroke begins. So this is an efficient flapping gait, and we're trying to mimic that with two modes over here. You can see on the left hand side, this is a kinetic sculpture. The two modes we're looking for is a flapping and flexion-extension. In this case, flapping corresponds to this shoulder joint moving up and down, and flexion-extension corresponds to this elbow joint bending and expanding. So you can see it how it works over here. So we have the shoulder goes up and the elbow tucks in. So this achieves like the wing folding that hopefully is more efficient than without. As So I'll briefly introduce you about the past work we did on biomimetic pet robots, flapping wing pet robots. We have here over here is P2. So I also try to achieve similar wing folding as Aerobat, but this is done through medial lateral movement. In this case, we have these 4-bar linkages expanding and retracting as the wing flaps, and it achieves wing folding by retracting these 4-bar linkages. Another difference that in the Aerobat, we're going to use flexible PCB membrane for the wing membrane, and we're going to redistribute some of these electronics on the wing. So some brief introduction on other existing flapping robots. We can categorize them as non-morphing and morphing wing. So on the non-morphing side, they're mostly on a smaller scale. This is basically micro aerial vehicles such as RoboBee and RoboFly. There's a medium-sized wingspan 30-40 centimeter over here, Robo Hummingbird and Descent Bolt by UC Berkeley. And there's a bird-sized robot over here, which has a wingspan of 60 centimeters, such as the Robo Raven over here. On the morphing wing side, they're mostly medium-sized robot, such as including B2, with a wingspan of 30 to 40-50 centimeter. Then we have larger scale robot with a wingspan of 60 centimeters, such as this Vesto Smartbird and this multimodal walking and flying robot by Tayar et al. So the robot with wing folding in the flexion extension is this Smartbird over here and Abdurrahim over here. So we're trying to achieve somewhere in this scale because the bat that we're trying to emulate is the Egyptian fruit bat, which has a wingspan of around 50 centimeter, and we want to keep it in this scale. So here's the presentation outline. So we're going to begin with the mechanical design. So this is how we design the monolithic arm wing structure, the kinetic sculpture. Going to more into detail the driving mechanism and some preliminary results. We're going to proceed to the gait optimization framework that we developed to get a better trajectory to match what we desired, and then we're going to finish with simulation on the finite element analysis and some sensitivity analysis, which we're going to close with the conclusion and feature work. So I'm going to show you this video about the concept design of Aerobat. So you can see here the Aerobat flapping with the kinetic sculpture to achieve wing folding and expansion. So we're trying to mimic the actual bat flapping gait, as you can see over here. Like the actual bat flapping gait has the wing folding during the upstroke, which you can see in the moment. We're trying to mimic this with this kinetic sculpture. So this is the exploded view of the internal mechanism. Like it's mostly driven by gears and cranks mechanism, actuated by a single motor. We plan to assemble this and try to test some of the untethered experiment at some point, but currently we're still in the middle of experimenting. So this is the kinetic sculpture flapping as it being driven towards the input arms. So this is the kind of motion that we want to achieve, and this is a close-up view using the microscope on the flexible hinges. You can see like that's a self structure and how it bends. So this is the motor section with the transmission gears, and this is how the overall structure will be assembled using the two kinetic sculpture. So here is the details on the transmission mechanism we use on this kinetic sculpture. So simply put, it's driven by a single motorized gear, which will drive some crank and gear and crank mechanism. So over here we have the forward mechanism to actuate the shoulder motion. So we have this gear and crank actuating the input arm up and down, which results in the shoulder motion up and down. Next we have the other forward mechanism to actuate the elbow joint. So similarly, the input on the input arm over here will actuate this link over here, which relative to the shoulder motion will actuate the elbow motion over here. So in total we have one motor, 17 joints and 12 links. Out of the 17 joints, like 11 of them are the flexible hinges. So here is the preliminary result trajectory that you can kind of see during the video as shown earlier. So the best result is using 78 derimeter material, and this resulting wing structure has a weight of 7 grams. You can see like this is during the downstroke. As it goes down, the wing expand, and this is during the upstroke. As this goes up, the elbow retracts. So this is the kind of motion that we want from our kinetic sculpture. So here's a plot of the simulated wing trajectory assuming a rigid link, like what we did on during the design on the SolidWorks motion study. So we have a pretty good resulting gait, but the problem is that we actually have an elbow hyperextension over here, which is very undesirable because like the wing could fold onto itself or like bend in a different direction during the folding and unfolding motion. So this is highly undesirable and want to fix this, and we can trying to fix it using optimization strategy. So here's the overview of that optimization framework that we're going to use. Simply put, we're going to optimize the wing conformation parameters such as the length of the linkages to follow this desired wing trajectory given parameter bound and geometric constraints. Because we're using 4-bar linkages, we want to prevent it from going singular, so this is that constraint that we're going to implement. So the trajectory itself, like is a sinusoidal motion, except that we want the wing to expand quicker than retracts. Especially want it to be partially expanded before the downstroke begins. So we simplify the problem by separating the shoulder angle and elbow angle parameters separately. So 13 and 17 parameters each. So here's the resulting trajectory of the optimized parameter. So there's about 60% change compared to the original conformation, and we achieve closer trajectory to the desired trajectory, which has no hyperextension. So this caps at 170 degrees angles, which is good. So next we're going to do finite element analysis on the wing structure to make sure that it doesn't break as it being driven around. So this is done using SolidWorks simulation, and these two parameter values are taken from the datasheet, but we don't have any information on parameters for Mooney-Livrin model that we're going to use. So we assume it has the same property as rubber, which is taken from Shashat et al. So here's a simulation result for the 70A durometer material done by SolidWorks simulation. At the beginning of downstroke, we assume that the bending is quite large at this moment. So has a maximum strain of 43%. So this material of 70A durometer has elongation at break at around 100%. So it has a good margin of safety margin for that. So here's another analysis done on at the beginning of upstroke, has maximum strain of 30%, which is less than the previous one. So it's quite unlikely that the wing will break unless we have many unmodeled forces, which probably came from the aerodynamic forces applied on the wing, but we have no idea what those forces should be without doing any wind tunnel experiment. So that has to wait. So here's some brief sensitivity analysis we did on this the wing conformation side. So it's like a change in parameter in the wing conformation will result to some change in the wing trajectory. So over here is a plot for sensitivity analysis for the shoulder joint trajectory. In this case, we're looking at the amplitude and mean. So a change in this any of these parameters results in some change in amplitude and mean of the shoulder joint trajectory. So you can see like some of the parameters actually has no impact on the shoulder joint trajectory, and this is quite important for one of our goal is to change some of these length parameters to control the wing flapping. So in this case, like two of the most sensitive parameters are this length over here, which is the length in this gear mechanism, and this angle over here. So the trend here is that the parameter near the driving gear is more sensitive than the rest. So here is another one for the elbow joint sensitivity. So still amplitude and mean to be compared. So similarly, like the parameter near the driving gear is more sensitive, but this time like changing the any parameter in the conformation affects the trajectory of the elbow joint. So from the previous results, like we can think of like there are some parameters that can adjust elbow, and there's some parameters that only adjust the shoulder joint trajectory. So basically we can adjust these parameters to achieve some desired trajectory to some extent. So this is a visualization of adjusting length 1, which is one of the most sensitive parameter in our design. So you can see like adjusting this by 10% plus and minus achieve this kind of variation in the final trajectory. It's quite hard to see here, but there are some changes over here as well. And then over here we have adjustment in length 4, which is a simple link that I believe like we can adjust this length if we change this link to like something like a string based linkage, for example. So there's some change in the shoulder joint trajectory over here. You can see the red. If you reduce this length, it reaches more towards the top, and if you extend it, it reaches more towards the bottom. And there's a huge change in the final trajectory on the elbow side. Finally, we have the parameter that only adjusts the elbow trajectory. So this trajectory has not changed, but we have a huge change in the final elbow trajectory. So that concludes it basically. Like it shows that there are some parameters that adjust some. It's possible to adjust some parameter to achieve some target trajectory to some extent. In this case, like maybe we can adjust the link 4 and link 9 to achieve like to adjust this trajectory for control purposes. So that's it. In conclusion, we have successfully developed a kinetic sculpture with a soft and rigid component fabricated monolithically using 3D printing technology, PolyJet 3D printing, and we have done analysis on the feasibility of this arming for an flying robot. And for the future work, we can assemble this wing and test it in a wind tunnel to get the lift and drag properties, and then we can implement this wing in an untethered flight. Thank you for listening and have a good day.